Hello, CCP2 students. This is Dr. K. This lecture is for Wednesday, January 27th, and I'm not here, so you're hearing me during class. And we're going through sections 17.1, 17-2. On Friday, I'll be leading you and going through some labs that we needed to finish up again. Then when we come back the next week, we'll keep going in chapter 17. So this is the only lecture or new material for this week. Chapter 17, sections 1 and 2, basically on how to make a buffer being a solution in which you can add a acid or a base and not change the pH very much, a strong acid or base. So let me go to the slides and tell you about the problems and stuff. Here we go. All right, so here we are. Date should be, and I'll have this copied over for you, 20 through 20. There we go. All right, so we're still in acid-base land, at least for most of the chapter, and then we go to something else. And we're still doing ice tables and stuff, but we're going to show how if we take a mediocre acid and its mediocre conjugate base, that actually makes a good buffer if we put them in the right proportion to each other. So leading up to that, we're going to talk about what happens to the pH of a solution that's either acid or base if we add the conjugate base at an appreciable level of that acid, or the conjugate acid of that base. So let me go here. All right. So this chapter is called Acid-Base Equilibria. Equilibria because we're going to be playing around with Le Chatelier's principle and trying to make acids less strong by adding their conjugate base and vice versa. And then later on in this chapter, we'll talk about solubility of ionic compounds and using ice tables for that. These are the ones that are barely soluble. If you remember way back to chapter 4, most ionic compounds are soluble. We're going to be dealing with the ones that are not soluble, but in reality, they're barely soluble, and we'll figure out how we can use some of the principles we've learned with ice tables to predict how much will go in solution, even if it's really little. Okay, so we're going to start with the common ion effect, which is section 17.1. What is it? So in chapter 16, we looked at the pH if there's only one solute. In other words, we put an HCl into water. And we said whatever the concentration of HCl is the concentration of H. We take the negative log 10, we get a pH. We do the same thing with a strong base, and then we can find the pH of weak acids and bases by looking at their Ka, doing an ice table, and so on and so forth. Now in chapter 17, we add another solute that has a common species. In other words, to a weak acid, we might actually add its conjugate base. So it almost competes. So it's like both directions are going about the same rate. So how do we find the pH in example? So we're going to do it kind of the way you would do from last chapter. And later on this lecture, we'll come up with a new equation in which we can find the pH of a buffer. If we add a weak acid and its conjugate base, if we know the concentrations of both, we'll be able to figure out the pH of it. So let's start out with this one. What is the pH of a solution of 0.10 molar acetic acid? Notice it has a low Ka, so we're going to have to do an ice table. But we also, instead of assuming we have 0 of its conjugate base, which is called acetate, by the way, what if we already added some acetate to it through sodium acetate? So what they're showing you here is, here's one of the equilibrium that we're dealing with, this weak acid. This is acetic acid right here that I'm underlying. And of course we can do an ice table and say, we have 0.10 molar of this. This would be 0, this would be 0. And we get x squared over 0.1 minus x equals Ka. What if we said, though, that instead of having 0 of this and 0 of that, we added its conjugate base? Remember, this is the conjugate base. And so when it's called sodium acetate, it's just a way to get acetate. Acetate, again, is the conjugate base of acetic acid. So what if we added something to that? So our ice table would be this instead. So since we have two things going on, we have the acid, of course, going from 0, 0.1 molar acid, 0. But now since we have this, since we have this, and this equilibrium, by the way, we're going to assume is very high, we're going to say we have 0.05 moles of this conjugate base in there. Whereas before, if we did last chapter, we would have said there was 0. So here's our new ice table. Instead of we'll have 0.10 here, minus x, 0.1 minus x. Instead of putting x here for the conjugate base, we're putting in that we already have something in there. We added some of the conjugate base. And so we put that in there. And by the way, we're going to add a little bit more possibly to it. And so we get our equilibrium expression equals x, which is our h plus, times 0.05 plus x. Notice that difference, it's not x anymore, over 0.1 minus x. And since it's 1.8 times 10 to the negative fifth, we'll assume that the x is small. So we get that. So what's all the whoop-de-doo about that? Well, if we solve for it, we're going to find out that the pH is a lot higher than it would have been without it. So let me go through this. What is the pH of this? And I'm sorry, it's the same question. The pH of the solution without the addition of sodium acetate. If we would have done this ice table and put in that we had 0 here, we had x squared over this. If we solved that one, we would have gotten that the pH would have been 2.87. But solving the ice table this way, where we have 0.05 to begin with, just trust me, comes out to be 4.44. So adding the conjugate base, what did it do? It made it less acidic. So this weak acid, it's weak because, strong acid would have been pH 1, is even weaker when you add the conjugate base. And if we end up adding enough conjugate base compared to the acid, we can get to the point where we're going to make a neutral solution, actually. So, conclusion, addition of a common ion in an acidic solution, in other words, the common ion is a conjugate base of a weak acid, shifts the equilibrium back to the left. It wasn't even going to the right that much to begin with, and lowers the ionization constant. What is that again? How much H plus comes off, and increases the pH. This is called the common ion effect. So, common ion effect is when a weak acid is added to a salt which contains the same anion. Okay, translation. It's the conjugate base conjugated to a cation. So for instance, here's HNO2. This is a weak acid. It's called nitrous acid. But if we add sodium nitrate, okay, so sodium nitrate, we're adding more NO2. We're going to push it back to the left. This is really Le Chatelier's principle. Let me go back and show this a little bit better. So Le Chatelier's principle would have said this. You're at equilibrium. You push this to the right. And now what we did is we added more of the conjugate base. So that makes sense actually to say that we predict that we're going to get things moving to the left then. So again, this guy right here, we're adding this. Le Chatelier's principle from the equilibrium chapter 15, says that then you move the reaction to the direction to relieve the stress, to relieve the increased amount of base, which means you're going to force it this way, and all of a sudden this H plus is going to go away, and you're going to get not as much of a pH. So you're playing around with Le Chatelier's principle, actually. So hopefully, if the class right now needs to take a breath, and you need to explain it, Miss Metaliano, go ahead and do that, and show them on the board that, Le Chatelier's principle is at work here. So I'll give you a minute. Okay, some more on the common ion effect now that you come back. So on this example, we have basically, I think this is acetic acid again. If we add more of this conjugate base to the solution, again, it's going to shift everything to left. So this is a weak acid. You're going to get, a relatively low pH, not as low as a strong one. If you add the conjugate base, since you're at equilibrium and you added more of the products, you're going to go backwards and go with more reactants. What does that do? Gets rid of the H plus to the H3O plus. So if we have this one, if we have 0.100 molar acetic acid, our pH would have been, by the ice table, 2.879. If we now add just a tiny bit of the sodium acetate, which we did before, it's 4.46. So anyway, so it's consistent with the Chatelier's principle. So anyway, how do you figure out those pHs? Basically, you do the ice table like we just did, except here, if we do it without adding the conjugate base, we'd put a 0 here, work it all the way through, take the get this concentration, take the negative log 10. But when we do it as a buffer where we add the conjugate base, we do the same thing. Solve for x, we'll get a different value, take the negative log 10 again. So that's how we get there if we do it by the common ion effect. Show another example of this. Here's sodium chloride, is at equilibrium and some KCl is added. Obviously, you're going to go left because you added more Cl. So when you do that, of course, the sodium will go down and you'll have more solid NaCl. What's my point here of doing this example? Well, pretend this was the conjugate base. This is an analogous example. And this was the H+. This is just to show you another way of looking at how the H+ goes down because you added too much of this. So when you add too much of this, you mop up this to make more of that. And that would be your acid, by the way. Cool. So anyway, we're already to buffers. So that was an example just to show you that if we have not a strong acid, but a weak acid and its conjugate base, and we add about this a pretty good amount, we can push the pH up quite a bit. And we can make the weak acid really, really, really weak, such that very little H+ comes in solution because we have a conjugate base that wants to eat it up. So, okay, what do we do with this? Buffers are solutions of a weak acid and its conjugate base. And so it's, as it says here, a solution of a weak acid and its conjugate base, kind of like they're both equal. One can give off H's, but then the other one is just is strong enough to mop it up. So it's almost like both of them are kind of kept in their tracks. They're like an even Steven, and the pH doesn't change. It can also be a weak base and its conjugate acid. It's kind of saying the same thing, actually. You're just reversing your names. Note this combination suppresses an already weak acid or base. Hence, buffers resist the change in pH because they're both at a stalemate, kind of like. Okay, example of how buffer works. This is just a proof in the pudding, so to speak. Here's another acetic acid and acetate thing. So we're going to put in 1 molar of acetic acid, but exactly 1 molar, a lot more this time, of its conjugate base. Of course, we got 1, 1, 1. We're going to assume that this guy's going to go to the right, and we're going to go minus x plus x plus x, and we have 1 minus x plus x over 1 plus x. Now, this might go by you a little bit, so let's figure this out. You're going to be surprised what you're going to find out in just a second that the Ka equals. It's a little bit of algebra going on in here. So if you put x and 1 plus x as your products, remember products over reactants, the concentration of product 1 times concentration of product 2, then 1 over minus x. But again, because your Ka is a weak acid, you're going to assume that x is really small. Guess what? This is really x times 1 plus x. By the way, you're going to put in a 0 here and a 0 here. That's the switch here. So if you put a 0, if you're going to put a 0 here for the x, you have to put a 0 here for this 1 plus x. Guess what you get? X. Okay, what the heck was x again? Basically, x is basically the Ka. And the Ka being x basically means that it doesn't change. So what did I just say again? It doesn't change. Okay. Basically, neither one's going to win. So let me do another way of showing this. So let's add 0.1. Okay, so we got that. So x equals the Ka. And the Ka is very, very small. So let's say the Ka is 1.8 times 10 to the negative fifth. Your x, your pH will be exactly that value. So, yeah, it's not going to be 7, but the Ka for this one is 1.8 times something like that, 5.8, I guess, times 10 to the negative fifth. Your pH is the Ka. That doesn't happen very often. That's a very small change, actually. That'd be a pH of 6 something. So anyway, now what we're going to do next, this is what we did in lab. We made a buffer by taking acetic acid, adding in this case, sodium hydroxide, but we added a conjugate base. Now we're going to see what happens if we added a strong acid to that buffer. So we already have this, and we said that, okay, so now we already have this table. I'm sorry, we already did this table. We said the pH is going to be equal to the Ka, and so that equals X. But now we're going to add 0.1 molar H+. Now what you're supposed to do is this. You're supposed to look at this when you do this work in this way. We're going to have a simpler way of doing this in a minute, so don't worry about this. This is kind of complicated. You're going to say that the acid here is a good guy to basically mop up any OH that comes by. And this one's a good one to mop up any H+. So when you have this guy here, the conjugate base, you're going to figure out how much of this is going to be used up. So it's kind of like this guy's here to combat any acid that comes in by, again, accepting the H+ that the acid spits off. This guy over here is kind of like the guy that says, if you send me an OH, I will add an H to it and make it water. So this guy mops up acids, this guy mops up bases. And there's 1 molar of each of it. So you can add up to 1 molar of your acid and 1 molar of your base. So anyway, let's add this much molar. So we do that, and we say to ourselves this. We say that now, if we add this acid, we're going to use up some of our mop. We're going to use up 0.1 of it. So we're going to make, and in doing so, we're going to make a little bit more acid, and we're going to get a little bit more and a little bit less conjugate base. Okay, so if you can follow me there. So when we do this, we get 1.1 when we add the HCl, and we got 0.9 now because we took away some of our buffer, and then we do the whole rigmarole here. And anyway, don't worry, we're not going to be doing it this way, thank God. But if we want to do it kind of like as a mathematician and use some logic, our pH now has gone to 4.66. So let's just trust that. Now, by the way, the initial pH before we added the HCl was 4.74. What am I supposed to prove here? You just added enough HCl to make the pH of water pH 1. When you add it to this system, the pH only went down by 0.06. And we saw that in lab, actually. So we added 0.1 moles of strong acid, which means we added 0.1 moles of H+. Now, if you take the negative log 10 of that, that's pH of 1 if we added that to anything else. But here, it only went down by 0.06. We got a great buffer. So anyway, buffers are made by mixing both a weak acid and a salt of its conjugate base, or by a weak base and the salt of its conjugate acid. And we just proved mathematically that they prevent drastic changes in pH. We added a strong acid that would have changed the pH to pH 1, but it only went down by 0.06 when we had a good buffer. So next thing, how are we going to, so the next problem is this. So what are we going to do with this? We want to be able to calculate pHs of buffers. How do we do that? So what we do, we have to introduce a couple things. So pH equals, of a buffer, when we add certain things to it, it's going to be the pKa. I'll explain what that is in a second. That's actually the negative log 10 of the Ka of the acid that's in your buffer. So again, we're going to take the negative log 10 of our Ka. So for instance, if our Ka is 10 to the negative 5th, well then our pKa will be 5. Okay? Then we're going to take the log 10 of the concentration of the conjugate base after we've done our thing. That's why we have to figure out how much conjugate base there is if we added something to our buffer, or the concentration of our acid that we had added in. So acid is the acid in the buffer, and the conjugate base is the conjugate base salt of the acid. pKa, again, is the negative log 10 of the Ka for the acid you put in your thing, and K is the equilibrium constant. Okay, so let's look at a problem here. We're almost done, actually. We're going to calculate the pH of a buffer made by taking 0.28 molar nitrous acid, remember that's not a strong one, and 0.23 of its conjugate base. So you can see that you have acid, and this is what you would have written down for its conjugate base. So you almost got equal amounts of both. The Ka for both is 4.6 times 10 to the minus 4th. So what you do is you plug and chug, of course. So the first thing you have to do is you have to take the Ka of the acid and take the negative log 10 of that. So negative log 10 of 4.6 times 10 to the negative 4th. If you do that in your calculators for a moment, you'll get 3.34. So again, the Ka is the negative log 10 of this sorry, the pKa is the negative log 10 of this Ka. So you find that first, and then you basically plug in these two values. So you have to remember it's base over acid, base over acid. You do have to memorize this formula for future quizzes and stuff. They don't give this on big tests. It's not a bad equation to memorize. It's just the pKa, and you have to remember who's over who. So it's base over acid, base over acid. Let's try another one though. Determine the pOH of a solution. Ooh. So we might have to get the pH and subtract it from 14, by the way. Maybe by mixing lactic acid. So we got the acid. And then we got the conjugate base of the lactic acid. So 0.25, 0.15, given the Ka. Solve using the Henderson-Hazelback. So again, base over acid. Take the negative log 10 of the Ka, 1.3 times 10 to the negative third. So what we got 2.886 for that one. Now I'll take the log 10 of our base, 0.150. Take the negative log 10 of our acid, 0.250. And we get minus 0.2218. So this is our answer. It's not too bad to plug and chug then. All right, so we're good with that. Now, that's when you're told how you made the buffer. What if you already had the buffer, but now you add some volume to it? You actually add a strong acid or base. Now you have to do some other stuff, which is kind of uncomfortable, to say the least. So buffer is prepared using what we just did. The pKa is 3.34. Did we get the pKa? I guess it's a little bit different. Let me see here. Yeah, there it is. It's actually from the previous problem. So I agree with the pKa was 3.34. Okay, so anyway, the pKa is 3.34. What is the pH of this buffer after the addition of 0.05 molar HCl? So now here's the uncomfortable part. So here's the buffer before, 0.28, 0.23. Here's the logic again. So we have to do this a little bit, but we're going to use the Henderson-Hazelback. But here's the deal. We're not going to put in 0.23 for our base over 0.28 because we don't have those molarities of those two again. You say, yes, we did. At the beginning we did, but we added this. So what we need to do is let's read this. 0.05 molar of the conjugate base will be reacted and used up to form an additional 0.05 molar of the weak acid. Ouch. So you have to take this amount and subtract it from the conjugate base, because the conjugate base will react with the excess H, and it will make an additional acid. So this is where we want to maybe stop for a minute and think about that. So we had this is our acid. If you want to write this on the board, the actual reaction, HNO2 becomes H plus NO2, and we have 0.28 of this, 0.23 of that. But now we're going to add basically HCl, which is like adding 0.05 of H. So if we add 0.05 of H, you're going to drive the reaction to the left to absorb what we just added. And so we're going to 0.05 of this is going to be used up, and 0.05 of the acid is going to be produced. So let's look at the new amounts here. So what we have, let's see if I did this right, 0.18. So the conjugate base should go from 0.23 to 0.18, and the acid should go up to 0.33. Whoops. I know I did something wrong, so my bad, you guys. Let me change this, and I'll have it changed in your notes. There we go. So that's what we got. Okay, very good. All right, let's go to another example. A buffer is prepared, using, whoops, we just did that. Sorry about that. We did that. Okay, cool. So we can calculate the pH of a buffer if you know the concentration of the acid conjugate base or base conjugate acid. Convert Ka to pKa if any other base or acid is added. If acid is added, subtract that amount from the base by the amount of the acid, then add this amount to the acid. If the base is added, do the converse. So, let's see. Let's try another one here. Calculate the pKa of lactic acid, given that when the concentration of lactic acid is this, the concentration of the lactate, its conjugate base, is this, the pH is 4.8. Okay, what do you do? So it says, fine. It says in this case, we're trying to find the pKa. So what we have is we have the pH, we have the amounts here, so yes, we can definitely rearrange this equation and solve for pKa and get the answer. So that's just another way to use this one. So anyway, the big one I'm worried about for you guys to think about is, again, when you have the buffer and you have the amounts, what if you added an acid? Can you rationalize that you have to change this amount down, the amount of acid you added? And for the acid, you go up that amount. So you have to change that ratio in your Henderson-Hazelback. Are you okay with doing that? So it might be worth putting this on the board and maybe thinking about this or a problem like it, and make sure you all feel comfortable with the fact that if you add something to a buffer that's already made, you have to recalculate how much conjugate base you have because it's used up, it's absorbed, and that you have more acid made. Again, that's when you add a strong acid. That will help you. Now, by the way, you can also look at the answer here and say, it makes sense. My pH did go down, but not by a lot. So hopefully that makes sense to you guys. Next video for Friday will be helping you put in some data for some labs we did before. So thank you very much.